This is section 14.6. And today, instead of thinking about our written notes as we have before, we're going to talk about IR spectroscopy and analyzing an IR spectrum. We're going to use this nice resource from the Michigan State University website. That is the chemistry department's website. I'll post this later in class resources. But essentially, every functional group has its own characteristic frequency, as we talked a little bit about before in 14.3, I think. And essentially, if we're clever enough, we could deduce the type of bonding that is present in a molecule simply by looking at the stretches in the IR spectrum. That is to say, if you see some stretches out here around 3400, you could say maybe that's an OH or an NH bond. Similarly, if you see a stretch here between 1700 and 1800, maybe you'll think that is a CO double bond. And you can really use the frequencies between 1500 and 4000 very well for this, because they have very small overlaps, and each functional group has its key frequencies. In fact, there's a whole table, and you can find tables and tables of this information on the internet in the stretching vibrations, which is typically found in the diagnostic region of the spectrum, that is 1500 to 4000. And let's say, for instance, you want to look at CH3, CH2s, or CHs. You could find those below 3000 typically. Are you looking for alkynes? As we said before, that could be around 3300 for the stretch. Similarly, CO double bonds like aldehydes and ketones, for instance, a saturated ketone where there are no double bonds, could have stretches between what looks like 1710 and 1720. If you have, for instance, a ketone in a ring, the cyclobutane, it goes out to 1780. So you can find a whole, you can find many tables of this information, and there's a table as well in your book that you do good to look at. In fact, I believe it's table 14.2 in your book. In fact, let's have a look at it now. There we are. Okay, so this is 14.2 in your book, and you can see that they give you the most important frequencies of IR stretches that we will use in this class. So it's a good idea to be familiar with this so that you can use these to find out what molecules are in an IR spectrum. There's a problem like this in your homework this week too, I believe. So, okay, back to our resource. Here we are. We can use these to deduce what types of molecules might be present just by the spectrum. So here is a typical spectrum, an IR spectrum of 2-butanone. Okay, so first thing we should find is 3000. That's always a good place to start. And if there's any peaks to the right of 3000, that means that we have CH bonds that are sp3. And if there are any to the left, that means we have CH bonds that are sp2 or sp. We don't have any high intensity peaks there. So, sorry, to the left of 3000. So it looks like we don't have any unsaturated bonds or sp2 or sp-CH bonds, which makes sense because 2-butanone doesn't have any. It only has sp3 carbons. The other thing we should find is the carbon-oxygen double bond stretch, which is a very strong stretch around 1700. And here it is. In fact, if we have a look, we can see that not only are there a few types of stretches, the CH stretches here, but we can see the CO stretch, as well as some much more difficult to spot bending vibrations of the CO. Mainly in this class, we're going to focus on frequencies to the left of 1500. So you won't have to worry about trying to deduce the properties of all of these peaks here. So again, have a look at the table in your book, which is table 14.2, as well as you could use this website too. It's very handy. Another website, which is very handy, is called the SDBS for spectra. It's a Japanese database that I learned about when I was an undergraduate studying IR. And it's really nice because you can type in into the database a compound name or molecular formula. So let's say we want to look at ethane. Okay, ethane does not have an IR spectra shown, but methylamine does. Let's look at ethyl alcohol. Here we go, ethyl alcohol. So the ethyl alcohol spectrum here, you see has a very large broad peak here that is likely due to the OH bond because of the hydrogen bonding interactions. We see that there is nothing to the left of 3000 because there are no double bonds or triple bonds, only things to the right. And there's nothing in that characteristic double bond region because there are no double bonds in the molecule. So using the many resources that you see here, hopefully you will have a better appreciation for how to use an IR spectrum to find what types of bonds are there. And this has been section 14.6.